So I just wanted to make a very quick recording on how you can model a DFB grating, so distributed feedback grating, which can act as mirrors and selective pass filters for optical frequencies, and how you can do this in OghmaNano. So the simulation we're going to look at is a demo simulation, and it's a two-period DFB grating. You can see there's one period here, and there's another denser period here. And these are used to just carefully select which wavelength of light you want to let through the grating. This can be accessed through the tutorials in the New Simulation button, Transfer Matrix method, and if you select Bragg Grating 1D. Now, the thing that's slightly special about this tutorial, about this particular demo, is that the light is coming from the side of the simulation, and this is a special feature of OghmaNano in that you can select to do the transfer matrix in any direction. So for example, if we go to the optical toolbar and go light sources, we can move the light source by selecting configure from the Z0 to the Z1, or to the top, or to the side, so you can have complete flexibility in which direction you want to illuminate. Obviously for this structure we want to illuminate from the left hand side, or Z0, because it's going to pass through the grating. So I'm just going to run it quickly just so you can see the output. You can see it doing simulation for each wavelength there. And if we look at the output, what we get is this. The first thing we look at is a device.csv, which effectively is sort of a 3D CAD geometry of how the simulation sees the world. You can see it's built up of triangles there. Then we get the optical snapshots. Oh no, that's not what I wanted. Then we get optical output. And this is a plot of effectively wavelength versus Z position. It looks a bit sort of bumpy, simply because there's a lot of points plotted there. We've got a complex structure, and the same for where the photons are absorbed. You're better off looking at, and that's just simply a function of plotting. You're better off looking at the reflected light, which is this. You can see we've got clear reflection bands, and the transmitted light we've got clear transmission bands. You can also see the generation profile, where you can see the absorption of the light in the different periods, and the gaps there is where there's air. I've toned down the number of sample points here just because I don't want the simulation to last very long. In fact, it's not the simulation that lasts long, it's the plotting that actually takes quite long, because it's quite a lot of data it generates. But if you want to generate smoother peaks, you just go to optical mesh, and you can bump that up from 100 points to say 200 or 300. It all look a lot smoother. Anyway, so that's calculating the transmission reflection spectra. So the question is now, how do we actually define this grid? Well, it's defined in two ways, and this is one of the nice features about OghmaNano. If you right click on this and go mesh editor, these dimensions here define the boxes themselves. Now it's a 1D simulation. It's not so it's a transfer matrix method projected actually onto a finite difference grid. So normal transfer method, you can read about it. Transfer matrix method, you can read about it. It sort of treats each object as a slab, but we're doing slightly differently here. Is we're discretizing the whole space using in the optical mesh with 3,000 points. But the point is that it's only a 1D simulation, so effectively it's only the size along that direction that really matters. It's not how wide it is that way, or how high it is that way. It's just the spacing that way. And before I go on how do we generate the structure, I'll just show you where the absorption is set. So the absorption is set in the absorption editor, and here we've got the absorption of silicon dioxide, and also the world, which this time we've set to air. You can set it to a polymer or whatever you want, but you can just select those materials from materials database. Now the clever bit is about how the actual structure is generated. So if you right click on here and go crystal editor, this allows you to effectively select how or define programmatically how the grating is made. So you don't need to click and drag things. You can set the spacing here. So we've got two periods of lambda 140 and 280, and we effectively define the periods like this. So supposing I wanted so clear points clears all the structures in the scene, add point adds a bar, and it's effectively just two simple for loops. So supposing we wanted half the number of periods for this particular for this second sub period, we put a 5 there, click refresh, and the whole thing updates. Now, to show or to include the effect of fabrication on this device, so fabrication sort of uncertainty, I've added a randomness here, and this is all Lua, so you can change this to your heart's content. So every time you refresh it, the bars slightly move there, and that's just so you've not got a perfect period, you've got sort of a non-perfect period. So with these tools, you can effectively design your own DFB grating and experiment to your heart's content. So I hope you enjoyed this video. You can download the software from OghmaNano.com, and yeah, thank you very much.